Hi, my name is Allison. In this course, we will cover the storage management lifecycle with availability intelligence.
What are the IntelliMagic availability intelligence solutions? Well, IntelliMagic Vision is our flagship product. It comes in several flavors for different product support. It comes in ZOS, ZOS Disk, ZOS Tape, and SAN flavors. And its goal is to protect availability and avoid performance problems with automated visibility inside your storage infrastructure. IntelliMagic Direction is designed to model the performance of your workloads on specific storage hardware configurations.
The learning objectives for this course are: define availability intelligence, discuss performance modeling concepts, and discuss the phases of the storage management lifecycle and how availability intelligence improves the outcome of the entire process through design, build, and run phases.
What is availability intelligence? Well, availability as defined by ITIL is the ability of a configuration item or IT service to perform its agreed function when required. Intelligence, as defined by Sun Tzu, is foreknowledge of an adversary. So what makes this powerful is when you combine the two, availability intelligence, which is the automated analysis of performance and configuration data using built-in knowledge about the hardware. What this does is it generates foresight, which allow you to protect availability. In this slide, we'll talk briefly about storage performance modeling concepts. Essentially, the goal of storage performance modeling is to solve the following equation. Configuration information plus workload information equals performance. The following picture is an abstraction of the configuration of a disk storage system. On the front end, you have host adapters, or in some cases called directors. Within the controller, you also have processor resources as well as cache resources. On the back end, you have a device adapter or a disk adapter, or sometimes referred to as a disk director. And then on the back end, you have the connected disk drives. An I/O workload consists of the following categories: reads, which can be broken down into random reads or sequential reads, random read hits or random read misses. On the other side, we have writes, which can be random or sequential, and the random writes can be random hit, meaning the record that's being updated is already in cache, or a random miss, which means the record that is being updated or the track that's being updated is not in cache. Sequential operations have the effect of cache hits because the controllers can do prefetching and read the data into cache before it's required. So these operations tend to have a lower response time than the random operations and require less disk operations. There are several sections in this diagram. The yellow section represents workload input. The blue sections are the internal components, and the green represents the outputs. So, to put it simply, the workload comes into the queuing model. There are adapter models, queue time spent at each adapter, and service times spent at each adapter. There are processor models. These are things like the Intel processors or customized ASICs or RISC processors that are embedded into the controllers. These have both a cost for the service time and queue time associated with them. And the drive models. So these are things like the speed of the drives influence these, the RPMs would influence these, the seek time. So each of the drive models is a reflection of the drive specifications and capabilities. Now, ideally, the models are built based on specifications from vendors as well as measured data from workloads in the wild. Each of the workloads will have a amount of time that they spent to be serviced and an amount of time that they spent queuing, waiting for the adapter if it's busy, or the processor or the drives. And the sum of the queue and the service time, the average queue and the average service time equals the average response time. Externally, we will report the utilizations, which is essentially how busy the different components are. So how busy the adapter, the processor, and the drive configurations. The individual models for adapter, processor, and drive will have individual response times or average response times, and the sum of those things can be accumulated to provide an overall response time. This, in essence, covers the direction product or modeling product at a high level abstraction.
In this section, we'll talk about the storage management lifecycle. Capacity management, as defined by ITIL version 3, is the process responsible for ensuring that the capacity of IT services and the IT infrastructure is able to deliver agreed service level targets in a cost-effective and timely manner. There are several processes that feed into the storage management lifecycle, particularly in the area that relates to capacity management. Initially, in the design phase, the architect or engineer will determine the requirements for the new system. During the build phase, the architect or engineer will initiate the build of the storage solution, and during the run phase, operations team will manage the day-to-day tasks of the storage solution. In each of these activities, there are specific things that should be done to ensure that the capacity and performance requirements are met. In the following section, we'll discuss those activities in more detail. During the design phase of the storage management lifecycle, the architect works closely with the business unit to determine the user requirements in terms of performance, availability, and cost. The architect or engineer also specifies workload characteristic requirements and requests the operations team to gather the workload information for any existing workloads. Then the architect or engineering team designs a system that meets the user requirements. In this section, I'm going to be covering several examples of design failures. The first example will be looking at when we underestimate the back-end disk capacity. We'll also look at an example where the front-end host adapter capacity was underestimated. And then we'll look at a cost savings example where a consolidation opportunity was missed. Lastly, I'll highlight the role of compression in terms of design failures. Let's look at an example of an underconfigured backend system. In the current environment, the customer is using 146 gig drives with a usable space of 100 terabytes and an IOPS of 70,000. This means that they had approximately 100 RAID groups or 800 DDMs with an average IOPS per spindle of 100 IOPS. When the user moved to a new system, they decided to implement larger disk drives, so they chose 600 gigabyte drive. With the same amount of usable space and IOPS, the required number of RAID groups was 25, with a total number of DDMs of 200. Now the IOPS per spindle was 400. This simply didn't work. So while the cost goal was successful initially, the performance requirements were not met. And because of the performance issues, there was an availability impact. So the overall result was a failure. In this example, we'll take a look at an underconfigured front end or host adapter. In this situation, the user decided that 4 ports on a single host adapter would be sufficient for their workload. Unfortunately, it wasn't. And as they started to ramp up their workload, they saw really large response times and front end port saturation. They had to purchase in an emergency fashion an additional host adapter. This additional host adapter allowed them to continue to perform well and grow their workload. So initially, they achieved the goal of keeping the cost low. Unfortunately, the single host adapter did not meet their performance requirements, and there was a significant impact to the user response time. So the overall result was a design failure. Oftentimes, when we're doing design of new systems, it's not so much the performance that we miss the target on, but it's the missed opportunities for cost saving. In this example, I'm going to show you how a 2-to-1 consolidation could have occurred using our modeling tool. So if you look at the chart, you'll see 4 stacked bars. The first 2 stacked bars relate to the existing generation of FICON systems. The next 2 bars relate to 2 different vendors that would both handle consolidation of the first 2 systems onto either one and provide better response time than they were currently receiving. In this case, the user chose to move from generation 1 to the next generation without any consolidation. The performance requirements were met, as well as the availability requirement. However, the opportunity for reducing significant costs to the infrastructure was missed. So overall, the design goals of the project resulted in a failure. Another example of a design failure is something that I came across with several different customers. You see, they were told that they could turn on compression and it wouldn't cost them anything. Unfortunately, the response time was so terrible that it actually impacted performance, and it cost them, at a minimum, user satisfaction. So rather than increasing the availability risk, I think it would be much better to plan and engineer those types of feature enablements before you deploy in production. Oftentimes, doing this in a test environment can be helpful, but not everyone has a test environment. So modeling provides a really low risk, low cost way to pursue this goal. There are many design challenges. In this table, I list a few. Which vendor do you choose? Well, the best practice would be to model each proposed option and use performance as a differentiator. But most folks tend to just get the newer version of what they have. Another category is trying to determine the right configuration. So you can take the vendor's word for it, which is the typical approach, or you can do comparative performance modeling of alternatives using specific workloads and hardware configurations. Another thing to think about is the lease term. Normally, people are just going to go for the best financial deal, but it's important to think about doing a forecasted modeling growth to determine the performance capability or capacity and determine when it will be exceeded. In terms of SSDs and automated tiering, do you just look at the vendor white papers and blogs, or do you have tools to help you understand it? Some vendors do, but if they don't, modeling the benefits of SSD and auto tiering is an excellent way to help you decide the optimal configuration. In terms of the disaster recovery configuration, typical approach is to take your best guess at your performance and bandwidth requirements. The best approach would be to model the impact of DR on performance and estimate the bandwidth required based on your historical data. When you're adding a new workload, what's the best thing to do? It would be best to model it to determine if the existing storage can handle the new workload. Typically, you're just going to buy new storage for the new workload or add some additional DASD for your existing workload. And lastly, when you're writing an RFP, you can leverage your favorite vendor bullet points, or you could utilize an independent approach that relies on deep knowledge of workload and hardware capabilities. One of the challenges when designing a storage system is trying to figure out which vendor would provide the best solution for your workload. Oftentimes, the incumbent vendor is the choice by default. But is that vendor the best for your workload? With IntelliMagic Direction, you can model your workload on different storage hardware configurations from different vendors and determine which one will meet your performance requirements the best. One of the daunting tasks when configuring your storage infrastructure is determining the best configuration for your workload. When you're designing a IBM SVC solution or storewise solution, one of the things that you have to do is to determine the number of node pairs. In this chart, we show the response time at different workloads for different node pairs. So the green stacked bar shows a 2-node pair, the red shows a 3-node pair, and the blue depicts a 4-node pair. And we can see that the maximum that the 2-node pair can sustain, the maximum I/O rate, is 154,714. And the maximum I/O rate that a 3-IO group node pair could handle is 245,714. Using this information, you can determine the exact number of nodes to configure to support your workload. When managing lease terms, people tend to think in terms of the cheapest or best deal they can get on a lease. They don't always consider the performance or where their system will be in terms of performance workload in 3 or 5 years that the lease determines. By looking at long-term trending information, you can determine your workload trend and you can forecast where it will be in 3 or 5 years. This will help you greatly reduce the risk of under-configuring your system. Almost every system on the market has some form of SSDs or flash technology, as well as auto-tiering to take advantage of the different types of disk storage on the system. But what is difficult to know without either doing a performance test or doing modeling is what is the best configuration for your workload. Well, with IntelliMagic Direction, it is possible to run your workload under a growth scenario and get the response times for different types of configurations. In this example, we show some XIV using 4 terabyte drives and no SSD cache. And we can see that's the steepest curve, and it's hitting the knee in the curve first, where it's just running out of capacity performance-wise. And we're also looking at XIV 4 terabyte SSD cache for 4 node pairs. And we're also looking at an XIV with 4 terabyte SSD cache and an 840 in the same pool in an easy tier pool. And basically for these workloads, there's no difference between the XIV and the pool that has XIV as well as the easy tier, but there is a difference between the XIV that does not have cache. When you're doing disaster recovery planning, it's important to make sure that you have sufficient bandwidth. How do you know if you have sufficient bandwidth? Well, if you have historical data, it makes it a lot easier to forecast the future. You also need to know what the distance is and what type of DR technology is realistic for the bandwidth and the disaster recovery goals that you have in terms of the recovery point objective and the recovery time objectives. Using IntelliMagic Vision to monitor your disaster recovery and using IntelliMagic Direction, which allows you to model your different types of disaster recovery conditions, allows you to get a really good handle on what you'll need and what you should plan for in terms of bandwidth and what you can expect in terms of RPO and RTO. So up until this point, we've really focused on the design challenges. In this next section, I'm going to be looking at the process of executing storage performance design with availability intelligence in mind. We'll look at how to gather the right configuration information, the right workload information. We'll look at defining performance requirements, and lastly, we'll look at designing a solution for managing the storage performance. When starting to design a system, one of the first steps is to get an idea of what your systems are doing. So we call that workload profiling. Really, it's just a fancy way of understanding what kind of IOs you're doing, what kind, are they read, are they write, are they read hit, what kind of response time do you have in the existing system, how many D stages are going to the back end. All of these metrics provide interesting and important attributes that describe your overall workload. In the next section, we'll talk about getting those right metrics at the right intervals and for the right duration. IntelliMagic Vision provides a unique way of viewing your workload profile. In this chart, I have a set of what I call mini charts that show the different key performance indicators such as the throughput, the IO rate, the various response times and cache hit metrics. And what's really interesting about this chart is that we have applied thresholds that are intelligent and context sensitive to help the user understand if there's any issues. So this is a great way to know if you're close to the edge of the capability of the box on the existing workload. It also provides an excellent way to summarize the workload for planning purposes. When collecting data, it's important to make sure you have data at the right intervals. That means utilize sensible intervals that capture representative workloads. In this example, we have storage pool throughput where it peaks at 7:30 when we use 30-minute intervals. The peak throughput at 7:30 is 1,882 megabytes per second. When we use 15-minute intervals, the peak is at 7:30 a.m. as well, and the peak is roughly the same, 1,892 megabytes per second. But when we adjust it to a 5-minute interval, the peak is 2,450 megabytes per second at 5:30 a.m. This shows the problem with using very coarse intervals. You miss out on the peaks, and so it's important to select an interval that captures those peak workloads. When profiling your workload, it is very important that you pick a measurement period that covers the peaks and valleys of your work. Sometimes workloads can vary significantly within a day, a week, or a month. It's important to look at a large enough time range that you capture those peaks and valleys. In this example, I show the danger of looking at too short of a period. First, we look at the data for a single hour. Is that a wide enough time selection criteria? Second, we look at a day's worth of data. Was a single hour enough time? No, of course not. We finally look at 5 days of data, and now we can tell if that single day was enough. Was it? No, it was clearly not enough, as there were other days with more significant workload. It's very important to look at enough data to capture those peaks and valleys. One of the most important steps that people often miss in the storage performance management lifecycle is the inclusion of performance requirements in an RFP. In order to do that, you really have to have a handle on the performance expectations of the users and the requirements of your environment. In order to answer the performance requirements, I have supplied several questions and a sample RFP performance requirement. What kind of performance have you had in the past? How many tiers do you have and will need? How much of each type of tier do you need for your workload? How much faster is the new storage for each tier? Will you be adding new features such as replication? What is the vendor willing to agree on? And how will it be enforced? How much capacity and workload will be added during the lease? One example of text that can be used in an RFP is this: a sustained average disk response time across all primary storage that is at least 20% lower than the measured data from current production systems while performing asynchronous remote copy. To summarize the process of designing your storage performance solution with performance in mind, first, let the vendors respond to the RFPs with your specific performance requirements. Second, compare the different RFPs based on performance requirements, cost, and features. Third, model and validate that each of the proposals will satisfy the requirements. Fourth, address any performance issues prior to build. And finally, select the vendor that best fits your price, performance, and feature constraints. In this section, we will look at how to incorporate performance into the build phase of the storage lifecycle. One of the first actions for the design team is to provide the build team with the information they need to properly set the service level attainment goals or service level objectives. SLOs are rarely operationalized because it's just too much work and it's too complicated. Instead of pre-configuring SLOs based on the actual performance requirements, users tend to lean on vendor when performance does not meet expectations. Unfortunately, this approach can lead to costly performance-related outages and even legal disputes with vendors. A better approach is to implement a solution that provides automatic performance evaluation based on your hardware and workload. Even if tools exist to provide some type of reporting or monitoring, rarely are processes and documentation created that allow the build and run teams to effectively manage the implementation of the SLOs. The best approach is to leverage a solution with built-in knowledge about the capabilities of the hardware and prevent the SLO violations rather than just reacting to them. This chart provides an example of how IntelliMagic Vision operationalizes SLOs. These are based on groups of volumes. These groups are often used to represent application. The chart shows key performance metrics across the top and the application names along the left side of the chart. Thresholds are set based on the expectations and requirements of the different applications. When thresholds are exceeded for a significant amount of time, more than 10% of the time that is, a warning exception is provided. The warning is depicted as yellow and the exception is depicted as red. The severity of the exception is quantified in the rating, which is displayed on the first line of the chart title. Any value above 0.3 indicates a significant exception to the threshold. In order to maintain the performance health of your storage infrastructure, it is important to understand what you can expect of your storage solution. While every vendor makes general and most often overstated claims about the capabilities of their solutions, it is rare for vendors to provide you any specific definition of the specific capabilities of storage you purchased. As such, it is difficult to know when your solution is running close to the edge. Sure, you know when things are performing poorly because the response times increase and the users start to complain, but at that point, it's too late. So how do you find out ahead of time if you are heading in the wrong direction? Well, if you implement IntelliMagic Vision, you will know when your storage controller is approaching its peak performance capacity because we provide detailed storage performance thresholds based on your configuration. This information is based upon years of experience modeling storage systems, and it's provided to our users as part of the solution. In this final section, we will look at the run phase of the storage management lifecycle. There are many benefits to incorporating availability intelligence into the run phase of storage management lifecycle. Let's review a few of them. First, monitoring applications. You can wait until problems are reported to take action, or you can get proactive alerts when storage resources approach utilization limits. Monitoring SLOs. These are often ignored or done in an ad hoc or reactive basis. You could do rigorous comparison of key performance and risk indicators and conduct service level audits before and after the install. Monitoring replication. You can involve storage and network vendors and try to moderate the discussion, or you can receive alerts proactively to identify potential problems and correct them before they become a major issue. Identifying root cause. You can send data, wait for the vendor, and hope for a resolution, or you can use built-in knowledge to quickly identify issues and drill down to the culprits. Monitoring imbalance. Imbalances can be treated as tolerated or addressed in an ad hoc basis, or you can proactively identify imbalances and make a plan to rebalance the imbalances. What this will do if you do use availability intelligence, it will mean a reduced mean time to resolution, and it will help you prevent predictable problems. The following chart shows how one could monitor application health proactively. In this example, the prod_db_oracle application volumes are being monitored. Thresholds have previously been configured based on the performance requirements of the applications. Volumes with front-end read response times higher than the warning or exception thresholds are noted in the legend. The most significant exceptions are highlighted in bold. This chart provides an example of an easy way to perform host and cluster service level audits before and after installation. In this chart, the weighted average of the host or cluster's front-end read response time is compared to the dynamic front-end read response time thresholds for this storage system for the workload that each host is initiating. The y-axis represents the percentage of intervals that the front-end read response times are good, shown as green, high, shown as yellow, or very high, shown as red. The x-axis labels are host or cluster names for the top 20 hosts in this environment. While simply reporting on replication can be pretty easy, monitoring replication SLOs is often difficult. IntelliMagic provides insight into the health of most synchronous and asynchronous replication technologies for supported platforms. The replication on this chart, particularly to West SVC 001 and East SVC 001, shows significant issues. The chart is red and the ratings are very high, especially to East SVC 001. Thresholds have been set that are appropriate for the distance and replication technology type. When a chart is this red, we know that replication is struggling to maintain consistency and the DR plan is in jeopardy. Even with the best solution, oftentimes identifying root cause is really hard. This is a case where the front-end read response time was really high between 2 a.m. and 12 p.m. the following day. The front-end write response time was high during this time also. Drilling down to the individual IBM SVC nodes, we could see that node 4 and node 5 were the most impacted by the read response time. Drilling down to node 4's ports, we can see significant buffer-to-buffer credit shortages during the same time period. We also noted a subset of the volumes had extremely high read response time. These volumes were all associated with the system named SYS0203. System 0203's switch ports were also saturated during the entire period. This is a classic case of a slow drain host. The host, which is running 2 4 gigabit per second ports, it's demanding more data from SVC than it can process. So when SVC opens up the fire hose and sends data back to the host quicker than the host can request it, the buffer credits get tied up on the SVC while SVC is attempting to transmit the data. There's several possible solutions. First, you could rebalance the host workload across additional host ports. Second, you could ensure that the host has the most recent HBA firmware and multipathing software, which may slightly improve the performance. You could also reduce the HBA queue depth on the host to limit how many outstanding IOs per second the host can send. This will have the effect of reducing the amount of outstanding requests that the host sends, thus tying up fewer common resources, in this case, the SVC node buffer credits. Lastly, you could update the host HBA ports from 4 to 8 gigabytes per second. IntelliMagic Vision allows you to quickly drill down and see the different types of conditions that can lead to the root cause. If you're one of the few organizations that manages imbalances proactively, congratulations. Most organizations manage by exception. It's not that they're bad people, They're just too busy executing more urgent requests, and those solutions they have to proactively manage balance are limited, so it gets pushed to the back burner. In this case, we show how easy it is to manage balance in an IBM SVC environment. First, let's look at the I/O group throughput balance across my SVC's I/O groups. Each bar represents an SVC I/O group. The average is represented by the green dot, and the green rectangle represents the standard deviation, though in our newer chart this will be the 10th and the 90th percentile. The yellow rectangle represents the minimum and maximum values. You can quickly identify any imbalance. In this case, I/O group 1 stands out, and if you drill down to the nodes, you can see that node 7 has way less throughput than node 6. Drilling down further to the ports, we can see that the port workload is not balanced either. If we want to rebalance the workload, we have to understand which system is doing what on each node. For this, we drill down to the read and write throughput by volume for each node, and this shows us the volumes that are actively doing I/O to each node. There's a couple of ways to resolve the imbalance. The easiest way, for platforms that support preferred path, which is basically everyone but VMware, modify the preferred path node for a few of the volumes to move volume activity from node 6 to the lesser utilized node 7. For an all VMware workload, ensure that the round robin is configured. This will ensure that the workload is distributed across the available nodes and ports. IntelliMagic Vision helps you identify the imbalances in your environment quickly and easily with enough detail to make actions and solutions. Managing the storage lifecycle with availability intelligence takes intentional steps throughout the design, build, and run phases of the continuously running lifecycle. During the design phase, availability intelligence activities include gathering workload and configuration information, defining performance requirements, and submitting RFPs that include performance requirements. During the build phase, availability intelligence manifests in the SLO definitions and enablement activities. And during the run phase, enforcing SLOs, proactively monitoring and optimizing storage infrastructure, and identifying root cause requires knowledge-based solutions that make these activities possible to do in an ongoing basis. If you have any questions, please send them to support@intellimagic.com.